visiting here from Rutgers and Flatiron CCA. And Alyson did her PhD in 2008 with Fabio Governado at the University of Washington, the N-body shop group there, studying galaxy formation in numerical simulations. And subsequently went to Caltech, where she was a Sherman Fairchild Fellow here for a few years, and then was a Granger postdoctoral fellow at Madison, University of Wisconsin-Madison, before taking a faculty job at Rutgers, where she's now an associate professor. And she's won a number of awards for her work, including Sloan Fellowship recognition for her teaching work, large computing grants, and most recently, as far as I'm aware, the Maria Geppert-Meyer Award from the American Physics Society for her work advancing theoretical astrophysics. And she's worked in that time on sort of almost all questions that you can probe with numerical simulations about galaxy formation and evolution. It's been my privilege. We were grad students at the same time, and we've been sort of peers, colleagues, sometimes rivals since then, but in the best sense of the word, where I think it's never been bitter, and she's pushed our group certainly to she's always pushing us, and I hope we sometimes push her. I usually feel like we're playing catch up to results that, you know, she published 5 years earlier or something, but you know, I think has really done a tremendous job both improving the field scientifically and improving it as a place for young people coming into the field to grow and become the next generation of leading scientists. So, thank you.
Turn this on. Thank you, Phil. Thank you very much for that very nice introduction, and thank you all for inviting me to be here today. It's good to be back. I came to tell you about work I am doing now to generate basically the large, well, it's mostly generated, the largest suite of dwarf galaxy simulations. And this here is a Milky Way mass simulation, but it is one of the highest resolution simulations yet published. And so what you see, this is a dark matter map of this Milky Way. Here is the host galaxy, but highlighted here are some examples of dwarf galaxies around this Milky Way. And I don't know if you can see it, but there really is a dwarf galaxy here, right? Because it's the highest resolution simulation yet published, we're pushing down into the ultrafaint range around Milky Ways. And so there really is an ultrafaint dwarf galaxy there, but I don't know if you can see it here in this lighting. Okay, so a little bit of history. It's been just over a decade, 13 years, since we were able to actually make realistic dwarf galaxy simulations. This is not the simulation, this is a real galaxy, right? But what I mean by realistic dwarf galaxies is bulgeless dwarf galaxies. When I got into the field, there was a huge discussion about the fact that every time we ran a simulation of a dwarf galaxy, it always ended up with a gigantic stellar bulge sitting at the center. Turns out no dwarf galaxies are like that. They look more like this. You know, this is NGC 6503, but the whole point is that it can be fit with an exponential disk all the way into the center. There is no stellar bulge. Okay? And so the big change, I wish I could say it was, you know, something amazing that we did, but really it was kind of resolution. Right? Resolution allowed us to get to the point where we were resolving high-density star formation regions inside of these simulated galaxies. That changed everything, all right? Immediately, the feedback impact changed. It started driving galactic winds from these dwarf galaxies, and then you could blow out the low angular momentum material that ended up sitting at the center and making a bulge otherwise. Okay, well, we're about to be challenged again, right? Even though we like to think we're doing a good job with the dwarfs, we're about to be confronted with a whole bunch of data that is going to challenge these models. So I wanted to highlight a few of these. The first, of course, is the Rubin Observatory's Legacy Survey of Space and Time. The other one here is the Marion Survey, which we'll talk about, and also Wallaby, which is an SKA precursor. So let me go through each one of these and show you how they are going to challenge our models. For LSST, right, it's really going to come in the ultra-faint dwarf galaxy range. So this is a plot I love to go back to from Tollerud et al. This is the radius to which we are complete for galaxies of a given magnitude. And perhaps not surprisingly, the brighter the galaxy, the further away we can see it, right? But for things in the ultra-faint range, we're not even complete within our own Milky Way, right? They are so faint that we can't even trace them out to the virial radius of the Milky Way. Okay, this plot's a little old, right? So these are the ultra-faint dwarfs we knew about at the time. We could add about a couple dozen more, thanks to DES down in this range. But you can see that a single LSST pointing is going to be deeper than DES. And if you stack the data over a few years, you're going to end up finding things that are about 1,000 solar luminosities, right, out to a megaparsec. Okay, so we're going to find tons and tons of dwarf galaxies. And this plot here is to remind us that it's not just because they're faint, right? That's not the only reason we haven't found them yet. The other reason is that we just haven't searched most of the sky, right? This is the Sloan Digital Sky Survey footprint, which was mostly pointed up out of the plane towards the North Galactic Cap. There are these tails down here in the southern hemisphere as well, pointing towards the Magellanic Clouds. And DES was also pointed in this direction. And so that leaves whole swaths of the sky that we haven't yet explored, right? And so the future is dwarfy. We're going to find hundreds of dwarf galaxies. And to prove that statement, when I keep saying hundreds, right, this is an example from Josh Simon, where he is showing the LSST stacked completeness limit here. And if we look at galaxies as faint as -4 and then come over here, right, that really is predicted to be hundreds of dwarf galaxies. Okay, that's in stars, right? That's the primary discovery there, is going to be stars. There's also this potential opportunity to discover dwarf galaxies through the gas. So this has actually been done. I'm not sure how many people are aware of the SHIELD survey, the survey of H1 and extremely low mass dwarfs. But the entire first sample in SHIELD was actually discovered in alfalfa. And then when they found these gas blobs in alfalfa, they went back to SDSS, found galaxies, but they were so faint or low surface brightness that they hadn't been tagged as galaxies in SDSS. Okay, and so here we've got a plot of H1 mass versus distance from the Milky Way, and Wallaby, right? Wallaby is going to push that down, going to push the limits from alfalfa down even further. And so it opens up this discovery space here to find all these low mass galaxies in H1 within a few megaparsecs of the Milky Way. And then the final one I mentioned is Marion. Okay, so Marion, by the way, is named after I believe, 18th century natural biologist who discovered that caterpillars turned into butterflies. And the Marion Survey is led by Alexei Leotodt and Jenny Green, and it is about to finish. It's ground-based. It's ongoing right now on DECAM. It should be done this semester. But there are specially designed filters that are targeting dwarf galaxies between about 10 to the 8 and 10 to the 9 stellar mass. And they expect to find roughly 100,000 star-forming dwarf galaxies in this redshift range, right? So just below redshift of about 0.1. And the really cool thing about Marion is that one of the main goals with Alexei as PI is to do weak lensing of these dwarf halos. So with stacking the dwarf galaxies, allows us to actually make some determination of the halos of these dwarf galaxies for the first time and do galaxy halo connections down to LMC sort of mass ranges, which is a new frontier, right? It's usually, so far, has only been done down to about Milky Way masses. Okay, so the things I wanted to talk about today, right? What are we doing? What are we going to learn from all these dwarf galaxies, right? So these two questions here sort of basically describe my career, right? So the first question, can we understand dwarf galaxies in a CDM model, right? We're about to be confronted with all this data. Will we understand what we find? Probably not, okay? But the other question also that I like to play with is CDM the right model, right? Not only are dwarfs excellent tests of feedback and star formation because of their shallow potential wells, but they're also dark matter dominated. So they're a great test of dark matter models as well. So if I have time, I will come back to that. But I am going to start here with this first question. And the first thing I want to tell you about is how we are confronting all of this observational data. Okay, so what you're looking at here is a volume of dwarf galaxies. So this is a zoom simulation. For those of you who are familiar with zooms, right, you run a cosmological volume. Most of the box is at low resolution, but you put all of your high resolution on a galaxy that ends up at the center, but you get very excellent internal resolution on that galaxy. We've done that, but rather than doing it on one galaxy, we've done it on dozens. And so that's what you see here. This is a sheet of dwarf galaxies, right? So this is a pretty big zoom simulation, but it allows us to get out dozens of dwarf galaxies. And we've done that 4 times, okay? So we are calling these our Marvel or marvelous dwarf volumes. Okay, you were just looking at Captain Marvel. But we have Captain Marvel, Electra, Rogue, and Storm. And together, you know, each volume provides dozens of dwarf galaxies. So together they provide about 100 dwarf galaxies. They are some of the highest resolution simulations in this range, right? So stellar masses, you'll notice star particles are born with 400 solar masses. And so that allows us to resolve ultrafaints in the field and ultrafaints that are satellites of other dwarf galaxies as well. Okay, so the Marvel runs, right, I said they were these cosmic sheets. They, in practice, end up being about 3 to 10-ish megaparsecs away from a Milky Way. So you can think of them in your head as being a good sample of local volume kind of dwarfs. And so to complement that, we want some galaxies near the Milky Way. And that brings me to the Justice League. Okay, so let me explain this one, right? We named the initial sample after Marvel comic book characters. So we thought we'd stick sort of with the comic book theme, right, and go with DC Comics. But we liked naming our simulations after women. Most of my collaborators are actually women. And so we decided that our DC Justice League, which in the actual comic books doesn't really have many women, would instead be the first 4 women who have served on the US Supreme Court. Right? That's our DC Justice League. So, all right. I would like to highlight, all of these have been run at sort of what I would say is the standard high resolution. It's what most people are calling the state of the art. Sandra and Elena have been run at higher resolution with star particles of 1,000 solar mass, actually 994 solar masses, right? So again, this allows us to push into the ultrafaint range around Milky Way mass galaxies. All right, and one more thing to complement those two, okay? Thanks to CDM, you end up with a lot more ultrafaints than LMCs, and so to complement that and to do some theory work for the Marion Survey, we are also running a bunch of Magellanic mass galaxies. So I'll play some movies. Here are 2 of those galaxies. We're still in the middle of running the full suite, but this is like my favorite part of the job, is running a simulation and then making a movie. So like I said, there's 2 different galaxies, but I'm also showing 2 different things in these movies. So on the left-hand side, this is a map of the stars and gas temperature in this galaxy. So the pinkish, purplish stuff that you see there, that's stars. They kind of are born blue and then they turn to red as they age. And you'll see some green, or sorry, not yet, you won't, but there's some blue stuff here. That's cool gas around this galaxy. And then you may see there's some green and red in feedback around this, as feedback goes off around this galaxy. This one over here is just gas. I'm only showing the gas, and it is color-coded by metallicity, right, with blue being the more metal poor and red being the more metal-rich stuff. But I just thought the colors in this galaxy came out amazing, and so I had to show this one. All right, so they run on for about 3 minutes, so I'm going to I'm going to cut them a little short and go on. Okay, here's the full sample minus the Marion galaxies. All right, so they're not on here yet. But taken together, this is the stellar mass of the simulated galaxies at redshift 0. This is their peak halo mass, right? So many of these, the stars in this plot, are satellites of other galaxies. And so we take the halo mass just before infall, or at a time when it's maximum, before it starts getting stripped while it's orbiting in the potential well of another galaxy. And so it's the peak halo mass. Also on here are some colors that are taken from different abundance matching estimates from other works, so you can see how they compare. And the main point is that this is the first big sample. I'll come back to that in a minute and show you how much bigger it is than other ones. And so this allows us to actually make predictions for what the slope and scatter is in the stellar mass to halo mass relationship for the first time with these simulations. So let me show you that. Here's our fit. Okay, so here's all of our dwarf galaxies. I should note, right, everybody at the above about 10 to the 10 halo mass, we're all constrained to the same thing, right? We're all trying to match abundance matching results up there. So this matches pretty well onto abundance matching relationships from the literature. But then we fit a break, okay? And so you might be looking at it going, really? 2 lines? You really think you can fit 2 lines? Which is why I've included this plot to try to convince you that there really does seem to be a break, okay? This is Sandra, our Milky Way, run at, we stuck with the comic book theme, right? So the highest resolution is mint resolution, like mint condition comic books, and the next lowest resolution is near mint. But this, I think, really, you can see here that there is a break at about 10 to the 10 in halo mass here in Sandra. And that's because of reionization, right? So it's not reionization, making these halos completely dark below that mass, but it is starting to suppress some of the star formation, and it has imprinted in such a way, that it creates this break. Now, usual caveats about some of these models apply. The reionization in these volumes is uniform, right? It happens everywhere at the same time. So it does not account for things like, are you in a low density or high density environment? And it also adopts the Hart and Maddow 2012 model, right, which is known to be fairly strong at high redshift. So with those caveats, right, there is still a break due to reionization. It would probably still be there with different models, but it may get washed out a little bit. Okay, so we fit this break, right, and here we assume below this line, essentially, well, we can fit the slope, but we're also fitting the scatter, right? We're assuming log normal scatter here, and you can see that it is growing as we go to lower and lower masses. It actually gets quite large, about a dex down here at the lowest masses. And we assume that all halos essentially should be occupying a galaxy. If it's dark in our simulations, it's probably just because we don't resolve it. Okay, so with all of that, we fit this slope and the scatter. And the reason we want to do that is to make a prediction for the stellar mass function that LSST is going to find, right? So if the scatter grows very, very large at low halo masses, that can impact the stellar mass function. And the reason that happens is because, thanks to CDM, right, there's more small things that can scatter up to be in bigger halos, whereas there's fewer big things that can scatter down. And so there's a bias in the direction, and that can change your stellar mass function. Turns out not much, right? Even with that large scatter at the lowest masses, here are our results for if you had no scatter, or if you had a constant scatter, or the growing scatter we actually found. And in the end, down at 1,000 solar luminosities, basically, we don't find too much of a difference in terms of how many faint things LSST is going to find. So, that's probably good, probably reassuring. Maybe we understand something about what we're going to find. Okay, let me then turn to a comparison with other simulations. So The black points on here are the Marvel and Justice League that I just showed you. Let's see. I mean, again, we're all trying to fit abundance matching results at the high mass end. So where we differ would be more down at the low mass end. There are a couple of exceptions on here that are well known in the simulation community. So you can see Auriga tends to make galaxies that are pretty massive compared to everybody else. That's, like I said, well known in the simulation community. I don't know how well known it is outside of the simulation community. And then there's also the other high ones on here are these Ravaz and Jablonka dwarf galaxy simulations. They are field dwarf galaxy simulations, but all their field dwarfs ended up becoming dwarf spheroidals. They used up all their gas and formed a bunch of stars. So they tend to sit pretty high in this relation. But otherwise, I'd actually say that, you know, with those exceptions, we are in pretty good agreement. And that's actually a different statement than some of the field has come to, right? There was a Nature Review article recently by Laura Salas and Andrew Wetzel and Ozzy Fatahi that actually argued that we were all disagreeing down here in the ultra-faint range. And I would argue, in fact, we just didn't have a large enough sample previously to see the scatter and see that we were all pretty much sitting within this scatter down at the lowest masses. Okay. Let me turn to H1. That was the stars. I also think we're doing pretty good in terms of matching gas fractions and gas masses in these simulated galaxies. So this is a very boring plot, but what you're seeing in red are FIGs, is the FIGs observational sample, right? So these are actual dwarf galaxies with H1 masses, and in black are the simulated data, and we seem to be doing pretty well at matching these low mass galaxies. So with that, let me turn to the size-luminosity relationship, right? That's what you are seeing here. Size being the half-light radius versus luminosity here. The black and gray points are local volume galaxies. Most of this data is coming from the updated Mechanici 2012 catalog, or if Munoz had a more recent fit, then we use that instead. But the blue and orange points on here are the simulated dwarf galaxies, both satellites and field dwarfs that come out of the two mint resolution Milky Ways, right? So Elena and Sandra. Here's our resolution limits, right? So here's the 50 star particle luminosity, and here is our half-light radius resolution based on our gravitational softening, and above that, we seem to be matching the data pretty well. Similarly, here is luminosity, but versus stellar velocity dispersion, okay? And so here is where I want to argue, you know, again, we've got the local volume data, and you can see where our simulations lie. We have things as low in stellar velocity as 2 kilometers per second. But to get there, you actually need the environment of the Milky Way, right? So I would argue that a lot of the diversity you see, including the size-luminosity relationship, including in this plot, is due to the fact that you've got things orbiting in a Milky Way potential. So if you come over to the right-hand plot over here, these are now, all these galaxies are color-coded by their peak halo mass. And what happens is, as a galaxy falls into the Milky Way and starts stripping its mass, that's what you see here. This is the virial mass it ends up with compared to its peak mass. So as things get stripped, they tend to move in this direction. And the things that end up with 2 kilometer per second velocity dispersions have lost, you know, more than 90 or 99% of their initial halo mass because they've been stripped so heavily. Okay, here is another prediction. There's a lot of information on this plot, so let me walk you through it. Now let me turn to basically focus on some of the ultra-faint predictions. This plot shows something that is, you know, either called T90 or Tau90. You're going to see it in a few of these plots. It's the time at which a galaxy formed 90% of its stellar mass. Okay, so we got T90 versus time at infall, and what we called infall was the time when a satellite fell into 2 RVir, because it can start losing mass even at 2 RVir, not just at 1 RVir. Okay, so you can see there's a number of galaxies here that sort of have almost a one-to-one relationship. They basically stop forming stars after they fall into the Milky Way, or a billion years or so after they fall into the Milky Way. But I'm going to focus on these guys. These are all ultra-faint dwarf galaxies. You can see T90 is quite old. They were done forming stars just a few billion years after the Big Bang. So these are your ultrafaints, right? These are the things that were shut off by reionization. But if you come down here, right, now we're looking at the mass of H1 in these galaxies when they infall. And the interesting thing is that some of these, they're done forming stars, right? They have no star formation going on, but they can still have up to 10 to the 5 or so in H1 when they fall into the Milky Way. So they are still gas-rich. This is the H1 mass over stellar mass as a function of distance from a Milky Way. And long story short, these are size based on their luminosity, but all the ones with red circles around them are ultra-faint dwarf galaxies that have enough H1 that they would be detected by something like Wallaby, right? And they are out in the field. So that's the first prediction, is that we're going to find gas-rich ultra-faint dwarf galaxies out in the field. Okay, so speaking of environment, let me come back to the stellar mass to halo mass relationship. Now, this is similar to the plot you saw before, but this movie is flipping back and forth. So let me see here. The circles are all centrals. They're all isolated galaxies. And then it's flipping to things that are backsplash. They have fallen into a galaxy and then back out. Or they are satellites. And you can see that there is a shift in the stellar mass to halo mass relationship between these two different populations. Okay, especially if you focus on the high mass end, you can really see there's an offset up there. And that is what this plot on the left is attempting to pull out in a different way. So now you're looking at the stellar mass to peak halo mass as a function of halo mass. But these galaxies are now color-coded based on their distance to a massive galaxy, where massive galaxy is defined as 3 times 10 to the 11 in halo mass. And you can see that you should see sort of a color gradient, where things on this side are more purple, and as you go down this way, things are getting more yellow. Okay, so it does seem to be that there's this offset in the stellar mass to halo mass relationship. I note that this goes away if you use total baryonic mass, right? So now here's the same plot with stellar mass and H1 added in versus halo mass, and now they all sit on top of each other and there's no offset. Okay. So for those of you who are used to thinking about things like the baryonic-Tully-Fisher relationship, this may not come as a surprise, right? That's basically what the baryonic-Tully-Fisher relationship has been telling us for many years, which is if you add in the H1 gas, you get a tighter relationship with the halo mass. However, all baryonic-Tully-Fisher work that I'm aware of today has focused on field galaxies and not thought about satellites. And I don't think there's any reason a priori that the satellites should have to lie on this relationship, right? So this is sort of new in that respect. Okay. That also results in testable predictions that we can test with observations. So here we have stellar mass versus, again, distance to a massive galaxy. Now everything is color-coded by this T90. Okay, so as you might expect, you see a lot more purple as you get closer to a Milky Way mass galaxy. That means that these things stop forming their stars earlier. And as you go away from the Milky Way, you see a lot more blue. Those are things that are still star forming. But you can see down here, right, these are our ultra-faint dwarf galaxies that are still gas-rich and, in fact, star-forming, right? That's a new prediction even to what I just said. They are still star-forming out here in the field. And, in fact, my grad student, Claire Riggs, made this lovely plot of the mean T90. She binned up the galaxies as a function of distance from a Milky Way, and plotted the mean T90 in each one of those bins, and you can see that there is a nice trend where the further away we get from Milky Way, The more recent T90, I apologize. T90 here is going to flip back and forth between age of the universe and look back time. I apologize. I will try to make note of that when that happens. All right, so now this means, more, the smaller numbers are more recent star formation, where on the previous plot, the bigger numbers were. I apologize. Okay. Any questions or comments before I go on? Phil?
Yes, I wasn't sure if you were going to say this, but is the trend in T lookback correlated with halo formation time?
Yeah, right. Thanks for asking that. So, yeah, it's yes. It correlates with a lot of things, it turns out. I had thought, this made sense to me, right? So in my head, well, I'm a theorist, so in my head, galaxies are Gaussian overdensities, right? So a satellite galaxy is a tiny Gaussian overdensity sitting on top of a bigger Gaussian overdensity, right? So it gets like a little boost from sitting on top of the bigger thing, and maybe that means earlier star formation. Further away you are, you're not getting that boost, so you have later star formation. All right, so that made sense in my head, and I had hoped it would show up in, say, concentration of the halo. Nope, that's like the only thing it doesn't correlate with. But it correlates with just about like every other way we can try to quantify these things. So, so it's not. I'm not quite sure what to make of this concentration thing, though. Yeah.
You said that you can see the impact of reionization in the stellar mass halo mass relationship, but that presumably that depends on what the reionization history is, right? And so,
yeah.
I mean, things which have Tau90s are presumably
right.
early reionization as opposed to.
Yeah, that's true. I mean, yeah, there's that caveat, right, where, it depends on which way we're looking at T90 here. But so when you say early T90, you're thinking ultrafaints around the Milky Way. It's also going to be a big overdense, yes. And so, all of this is with that caveat that, we don't have reionization happening at different times in different places. So it will have some impact on that. But I think these trends are robust even to those changes, right? Because they go in the direction of the things in the field will probably still be star forming. Yeah.
Okay, so this is a simple question. If the mass of a stellar particle is just 1,000 solar mass, then some tails will contain less than 100 particles. So do we still have reliable subparticle physics, and can we still extract the dynamics of these galaxies? So in this mass regime, supernova explosions will be highly discrete. So
Yep. Yeah. And so the same grad student who put together the results from the ultrafaints in the field and the ultrafaints around the Milky Way also implemented a stochastic IMF, so that we are actually keeping track of individual massive particles and discrete supernovae that go off, and not sort of averaging them out. Is that what you were getting at?
okay.
Yep.
Great, thank you.
Yep. Yeah, I've just swept every simulation detail to the side here to try to get at the results. So feel free to grill me on that later. Okay. Another result I wanted to highlight here is on the age of dwarf galaxies. The age gradients in dwarf galaxies. Okay, so in the Milky Way, many of you are probably familiar with this idea that the Milky Way has grown from the inside out, meaning that the older stars are sitting at the center, the younger stars are sitting on the outskirts. It turns out dwarf galaxies look totally the opposite. Okay, they look like they formed outside in, meaning the younger stars are all sitting in the center, and the older stars are sitting on the outskirts. And this is true no matter what type of dwarf galaxy you look at. It's true in the satellites, it's true in the field, it's true in transition dwarfs, it's true everywhere. So environments, whatever's making this happen, it doesn't seem like environment is a satisfactory explanation for how this outside-in formation came to be. You can kind of see it here. This is the Phoenix dwarf. You can kind of see it here, right? There's a lot of blue stars sitting at the center, and then it gets a little red on the outskirts. In case you can't see it, I'm going to guide your eye. It looks like that. But here is a simulated dwarf galaxy. It's got a stellar mass of about 10 to the 7, so something like WLM, let's say. And what we've done here is bin up all the stars in this simulation according to age. So 14, these are our oldest stars, right, between 13 and 14 billion years old. And the youngest stars are down here, between 0 and 1 gigayear old. And the y-axis is actually the average formation radius of stars in those different time bins. So if you look at the oldest stuff, right, it formed closest to the center. And as you go up this way towards the youngest stars, they form further out. So that's an inside-out formation. However, if you look at where those stars end up, right, the oldest stars may have formed closest to the center, but they actually end up the furthest out. So they look, if you look at them at redshift 0, they look like they formed from the outside in, but they actually formed from the inside out. Okay, and before I get to why that's happening, I just thought I would show the full range of the simulation results. So we have here things from basically ultrafaints up to LMC masses. Satellites and field dwarfs are essentially doing the same thing, which is good because that's what they do observationally. But there's sort of this U shape, and where now we have T90, right? And it says explicitly time since Big Bang, right? So here's the more recent time down here at closer to 14. But on this axis, on the y-axis now, this DT90, that's T90 if you measure the center of the galaxy and then do it again at the effective radius and then take the difference, right? And then you get a slope, basically an age gradient between the center and the effective radius. And so you get this sort of U shape where things that have T90 about 7 or 8 billion years after the Big Bang are the best at ending up with steep age gradients. As you go towards younger things, you sort of wash out those gradients. And as you go towards the older things, right, the ultrafaints, you wash out those gradients again. Okay, so what's going on? Well, to first order, we think it's the same process that makes dark matter cores. Okay, so for anybody who's unfamiliar with this idea, here is a simulated dwarf galaxy. You are just seeing a temperature map of the gas in this galaxy. And this is a movie that runs, I think, about 500 million years. But in that time, this dwarf undergoes several bursts of star formation. If you watch it, there's like, here we go. There is a big burst that the supernovae heat up the gas, and you can see it coming out in these red flows. The dwarf, I should note, is about a kiloparsec in size. So it's sitting down here, and it's edge on, but you really can't see it at all. That bursty star formation is sort of famous for influencing the dark matter, right? So this is the same dwarf galaxy. Now you're looking at the dark matter density as a function of radius in this dwarf. And as it starts at high redshift, you'll see that that line is very steep. It's very cuspy. This thing has, an NFW cuspy profile. And then with time, as it undergoes bursts of star formation, that actually flattens into a core, and you end up with a shallower density profile. And so what we think is happening there is when you see all this gas evacuate from the center of the galaxy, it's actually fluctuating the gravitational potential well. So essentially, the gravitational potential well flattens, the dark matter orbits expand. Later, that gas can cool back on to the center of that galaxy, so they'll contract a little bit, but the initial outflow is impulsive. All right? It's not adiabatic, and later that cooling is adiabatic, and so it doesn't come back to where it started. The dark matter doesn't come back to where it started. And so you essentially do this over and over again. You keep pushing dark matter out of the center of the galaxy, and you transform that cusp into a core. All right, well, dark matter is collisionless. That's what this is, collisionless particles in the simulation, and so are stars. So whatever's happening to the dark matter should also be happening to the stars. And so to first order, we think that's what's happening. So if you look at this left-hand plot here, now I've got the slope of the dark matter density profile, where things down here at 1.5 are very steep, they're very cuspy. Things closer to 0 are cored. And here we have the age gradient, so this is DT90. So 0 is basically a flat age gradient. If you focus on these galaxies right here, you can see they're very low mass. They are not galaxies that are very bursty, right? So galaxies at about 10 to the 8-ish in stellar mass are really, really efficient at having this bursty star formation over and over again. But as you go down to these lower mass halos, they're not. They have like a burst and then they're done. And so you don't make a dark matter core, but as you go up this way, right, you start going to higher and higher mass galaxies, And so you get this burstier star formation. You start making a core, and that sort of explains this trend this way, right? As you head up sort of diagonally in this plot, you get things that are more cored, and they have managed to create these steep age gradients through this gravitational potential well fluctuation. Of course, you may also be looking at it and going, yeah, but what about all this? You've got a bunch of galaxies up here that are actually cored, and yet they have this whole range of age gradients. What's going on there? And that is what the right-hand plot is designed to draw out. If you look at these cored galaxies up here, these are now colored by T90. Is that off the edge of the plot there? That's T90, where 13 is recent, right? Recent star formation. And so these are older than these galaxies. And so what we think is happening is as you move in this direction, if you've had more recent star formation, you're essentially lighting up the dwarf everywhere, and it's erasing any age gradient. And so that's how we sort of get these two different trends in this plot. Okay, now, I would be remiss if I didn't mention that fire has also looked at these age gradients, right? So I just wanted to compare quickly to fire. Here is the exact same thing. It's the age gradient as a function of T90. And now I've got dwarf galaxies from fire on here in gray stars. Fire only looked at field dwarfs, not satellites, above 10 to the 6 in stellar mass. And so we're limiting our sample here to the same thing for comparison. And you can see we basically agree, right? There's pretty good agreement here in terms of what to expect. The thing that I find interesting is that if you use T50, the time when the galaxy formed 50% of its stars, that is no longer true, right? So here is the result from Gauss et al. Showing the slope, the age gradient, as a function of T50. And essentially, it looks just like the T90 result. It doesn't matter if you use T50 or T90. Here's our same result using T50, and it's a total scatter plot, right? And again, we'll come back to this. This is look back time. This is the age of the universe. I'm sorry. So you should flip that axis if you want to compare directly. But since one's a scatter plot, it's gonna stay a scatter plot, right? So basically, what this says to me is that whatever process is setting the age gradients in the fire dwarfs is done. It's already happened by the time 50% of the stars have formed. But in our galaxies, it's happening later. It's happening between T50 and T90. I don't know, but I suspect this could be the reason why. This is a result from Karim El-Badri's work in 2016, where this is one fire dwarf where he's plotted the specific star formation rate. You can see this thing is very bursty. It essentially undergoes a burst of star formation and then quenches. But he plotted up the radial velocity of the gas, all the gas, and the star-forming gas, and you can see it matches really well to the star formation history, right? It's being pushed around by the feedback processes that that are happening in this galaxy. And the stars are as well. So here are the young stars in blue. They're being born in that gas that has these radial velocities. And we have verified that we don't have this. So our young stellar velocity dispersions are below 5 kilometers per second. They're very low. And so we are not having the same process. So if this is influencing the age gradients, that might be where the difference is coming from. And the main point here is that if we can measure this, and we can, in theory we can, with resolved stars, right? If we can get fit resolved star histories to measure T50 and get an age gradient, so you have to do that as a function of radius in the observed galaxies, we have an immediate test, right, between these two different models, which is kind of a nice observational thing to go for. And with that, I was actually going to switch gears a little bit, so maybe I should stop here and see if anybody has any comments or questions before I switch gears.
Ask a super technical question.
Oh gosh, all right.
These all use the blast wave model, or?
Yes, they did. All the new ones have the superbubble, and so far we have not found any difference between the blast wave and the superbubble in terms of galaxy properties.
Any predictions for the existence of black holes in the middle
they're there. They're in. I'm not talking about them at all today, but I had a PhD student who wrote many papers, 3 papers on black holes in dwarf galaxies. So they're in there. We have a model where black holes are seeded. They're trying to mimic the direct collapse models where if you have a converging flow at high redshift and metal-free gas that's kind of warm so it doesn't fragment, it can directly collapse into a black hole. And so that's what happens in our simulations, and then we just track where that black hole goes as a function of time. So far, though, we haven't seen much of an impact on these galaxies. So.
And why doesn't the feedback from gas accretion on the black hole change the dark matter slope?
It's just not. There's not enough of it. It's very low luminosity accretion essentially at this point, and it's not fluctuating the gravitational potential well. So it needs to fluctuate the gravitational potential well in order to have that impact. Okay, I'm a little uncertain actually if I should. Okay, about 10 minutes. I think I can talk about dark matter in 10 minutes and make sure everybody's out of here by 5. But I wanted to switch, like I said, and talk about the other half of my life, which is thinking about SIDM these days. And so I'm going to motivate this by talking about the diversity of rotation curves problem. All right, so if you haven't heard of this, this is the original paper that invoked this problem, Kyle Oman and his collaborators in 2015. And so what you see here, this is a nice example showing the problem. In green, these were simulations from Kyle's set of simulations, which did not make dark matter cores. And so they're somewhat steeply rising, and then they get flat. The red data points are actually 2 of my dwarf galaxies. One of them was in the core movie that I showed you earlier. They're less steep, but maybe not as shallow as you might expect. But then here's a real galaxy, IC 2574. Here's the data. It's very slowly rising. Right? And so what Kyle did is he quantified this by looking at the velocity at 2 kiloparsecs, right, as a measurement of the inner slope compared to Vmax, the outermost rotation velocity. And that's what you're seeing here is a whole bunch of observed galaxies. And Kyle's point was, it's not just making slowly rising rotation curves, which was sort of the challenge for many years and why we all got excited when we made dark matter cores. But there's also all these steep galaxies, right? All these steeply rising galaxies, these really dense things. There's a diversity of rotation curves. And so here's how simulators have responded so far. Here is Nihao. Again, here we've got velocity at 2 kiloparsecs versus the outermost velocity. And the blue, or the cyan this time, are all real data. And the gold is the results from Nihao. Okay, so what they concluded was we can make these shallow things. We can make these things that rise very slowly. What they couldn't do was make the ones that were circled here in red, right? So these are the things that are where the rotation curve is rising very fast, and these things are very dense. And they went, so there you are. Here is a more recent result showing essentially the same thing from Roper et al., where this is a simulation where they make dark matter cores, just like in Nihao. Now, rather than v at 2 kiloparsecs, they are plotting this fiducial velocity. The idea is that it's still a measurement of the innermost velocity or inner velocity, but now it scales with galaxy mass, and so that's the equation for it up here. But again, as a function of the outermost velocity. In black, X's here are real galaxies. Okay, so that's the data they're trying to match. The the circled in black squares are their simulated dwarfs, and this is the results. These are the velocities you get if you just look directly at the simulations. You play God, and you just take the result right out of the simulation. The circles, on the other hand, is they've done a whole bunch of mock H1 of these galaxies in order to try to more directly compare to the observations. But their point is, you get a broader scatter when you do that, but you still don't make these most dense galaxies. Okay. However, they said, if I don't make cores, these are the exact same set of simulations here, and instead of letting core creation happen, they didn't let core creation happen. All you have to do is change your star formation threshold to make that happen. They said, look, in that case, we actually do match the observations. Okay, so that's actually the current state of things. All of these dwarf galaxy simulations that we were so proud of making, these shallow, they're slowly rising rotation curves and dark matter cores, have not been shown to make the most dense galaxy rotation curves. That is the state of the field at the moment. Okay, so that is where SIDM comes in. Right, and so I know astronomers love their CDM, so I always like to motivate this with something we're more familiar with, which is the standard model, right? So ordinary matter, the stuff that makes up you and I, right, is actually really complicated. There's a lot of particles in the standard model. And instead, when we talk about dark matter, we always picture this one particle, right? There's one particle, it's really simple, it does this one thing, it only directs through gravity. But there's no reason that dark matter has to be like that, right? It could be just like this. There could be multiple particles. There could be a whole dark sector or dark side if you want to, play around with that. And there could be a mediator particle, right, where two dark matter particles can exchange energy between each other. That's where this dark photon or dark light or dark radiation comes in. Okay, and so that's the idea. I sort of like this philosophically. There's no reason that dark matter has to be so simple. There's a great example of it not being simple. So Manoj Kaplinghat and his collaborators have sort of been famous for showing that SIDM does an amazing job of matching the diversity and rotation curves. So what you're seeing here are a lot of the same, galaxy data that we've seen before, but now they're divided up into different bins. So roughly between 80 and 90 kilometer per second galaxies here, 90 to 136, and so on. The data, the actual data, are the data points with error bars, but the lines that are fit into all of these are a fit using a self-interacting dark matter model. Okay, and so their argument is I can totally match the diversity and rotation curves if I use SIDM. And the reason that happens is because SIDM makes cores as well. All right, so all the scattering essentially flattens the dark matter density in SIDM as well. And then you end up with this gravithermal, a halo in gravithermal equilibrium, and it responds very well to the baryons. So if the baryons come in, maybe say do a galaxy merger or something and get pushed towards the center, then the dark matter responds very well and comes with it. And you end up with things that are really, really cuspy or dense or steeply rising, however you want to put that. Okay, so here's where I'm at with my sample, all right? And this is part of the reason, again, why we're running these new Marion Magellanic galaxies. The red points here are, this is the diversity rotation curve problem. These are the data from Marvel and Justice League so far, compared to the observations in gray. And there is one thing. Honestly, this is doing better than every other simulator that I'm aware of, right? We have one cuspy, steeply rising thing, but it's not very satisfying when you only have about 5 galaxies in that mass range. So we're trying to add a bigger sample to see if this is consistent, and then we're going to do it all again in SIDM and see if that does better. Okay. So I just want to advertise what we're doing there because I was at Stony Brook a couple of weeks ago, and their biggest concern with SIDM is they said, well, that just opens up the parameter space, right? You can sort of fit anything you want to make it all fit. I'm going to argue that that is totally not true. Okay, and the reason it's not true is that self-interacting dark matter is highly constrained these days, and that's because of the ultrafaints. What you're seeing here is the density of measured, right, measured from satellites in our galaxy as a function measured at their half-light radius. The black lines going through all of them is actually the results from CDM simulations. Okay, so what's going on is that the ultrafaints are super dense, right? They're very dense, and in CDM that comes out naturally because they're the first things to form, right? Small things form first, and the earlier you form, the more dense you are, and so you get these really dense ultrafaints. If you want that to happen in SIDM, you have to have a very high cross-section. The cross-section, in fact, has to be so high that not only have you made a core, but then you actually, it becomes energetically favorable for you to undergo core collapse. And you end up being incredibly steep or dense in the center. Okay, so this is a lovely result from Correa et al., where she took the individual data, density data from each of these dwarf galaxies in our Milky Way and asked what is the cross-section for interaction you have to have in SIDM as a function of their velocity in order to fit all the data. And this is what came out. And the right hand is a bigger picture here, where here are the dwarf galaxies. We have constrained at cluster scales that the interaction cross-section has to be very small. It's usually taken to be less than about 0.1, in fact. And so if SIDM, and in the middle, right, somewhere in the middle, it has to be around 3 to fix the diversity problem in rotation curves. And so you have to have this steeply rising velocity-dependent cross-section. It's like the only thing allowed in SIDM. Right? So if you are going to be running these simulations, you basically have to use this cross-section in order to match all the data. And so that's what we're doing. And I just wanted to highlight that one of the first things we're going to be looking for is actually galaxy shapes. Right? So if baryons make cores and SIDM makes cores, then cores aren't useful. But because of the scattering that happens in SIDM, you actually end up sphericalizing the inner halo, or even maybe seeing the effects further out, depending on the cross-section. Whereas in CDM, you always get these triaxial prolate halos. There has been evidence that the stellar shapes that come out of these simulations traces the underlying dark matter very well. This is one result using the fire dwarf galaxies, where you're looking at the axis ratio of these galaxies. So C would be the shortest axis ratio, A the longest, B the intermediate. But the whole point is that these dwarfs end up being fairly prolate, just like in their stars, just like the underlying dark matter. Okay, so in the end, what we're going to be looking for is, in the ultrafaint range, baryons shouldn't make cores. If you see cores in ultrafaints, it's not CDM anymore, it's not baryons. Something else is going on. But let's assume these are going to be cuspy dwarf galaxies down at this range. If they're sitting in spherical halos instead of triaxial halos, that points to SIDM. And the same thing up here. Now, if you get up to about 10 to the 8 in stellar mass, right, there are actual observations on here. These are all cored galaxies. We don't know if it's baryons, we don't know if it's SIDM, but if we can measure the halo shape, then that can tell us if it's maybe CDM or SIDM. And there actually has been this wonderful first work on this by Gigi Leung and Ryan Lehman, where they looked at WLM and found that it is a core dwarf galaxy that looks like it's sitting in a prolate halo. Okay, so that's some very nice work. And it's 5 and I'm done. Okay, so that's my conclusions. We're running this large suite to make all these tests, observational tests, but also to take a look at dark matter. And I'll just stop there and let people ask questions. Thank you. Yeah, I mean, our Milky Ways are forming inside out. I mean, everything's forming inside out, technically, right?
Do you have any proposal why is it so different than the Milky Way?
So in the Milky Way, right, if core formation is the same, is the process that's doing it, that's setting these age gradients, core formation fluctuates sort of the inner kiloparsec of the gravitational potential. But in the Milky Way, right, you're forming stars out at 10, 15 kiloparsecs. You're not fluctuating the gravitational potential out there. So you're not kicking stuff out to like these large distances. So instead, it looks like things are forming inside out if you're looking out to these large distances. Does that make sense? Sort of. And maybe if you look in the inner kiloparsec, but yeah.
Grab Alyson in a moment. Some more questions during the middle. Let's go to wine and cheese, and you can catch Alyson there. And thank her one more time.